Hello, let us see a few board examples of NP-complete problems. First, let us do a couple of difficult proofs, then we will have some simpler reductions. Let us look at this problem. The Vertex Power problem. Let me introduce what it is. Let G B, E be an undirected graph. Then a subset U of V is called a vertex cover of G if for all edges U, V in E either U or V or possibly both belong to U. Okay. So it's essentially a set of vertices, a subset of vertices that covers all possible edges in E. Okay. So usually we are interested in the optimization problem called the minimum vertex power problem. Which wants to find a U whose size is as small as possible and which covers all the edges. Okay. But this is an optimization problem, so we have this decision version of this. Given G and positive integer L, decide whether G contains a vertex cover of size, that is the number of vertices in U. You may actually say equal to L, or you may also have less than equal to L. Does not actually matter. Anyway, let us work with this equal to L version. Okay. So, I will now prove that this is an NP-complete problem. First thing is that vertex cover is in NP. Why? Because if the graph actually contains a vertex cover of size equal to or less than equal to L, then just produce that subset U. And then it is an easy matter to check whether that subset actually covers all the edges of the given graph. So it's definitely and trivially in NP. Okay, so for NP hardness, I will use reduction from let's say CNF set to vertex cover. So that means, again, given a Boolean formula phi in the conjunctive normal form, I will create an undirected graph G, and I will also specify some L such that G has a vertex cover of size L if and only if phi is satisfiable. Okay. So, like the Hamiltonian path problem, I will have something like a vertex gadget. Sorry, I should call it, this contains clauses and variables. So we have a variable gadget. And we will also have a clause gadget. Now the variable gadget looks like this. If xi is a variable or x is a variable, x complement, I will take two such vertices in the graph G and I will simply connect them. And if we have a clause like y1 or y2, yl, or maybe size is s, then I will have the clause gadget will look like a complete graph on s vertices labeled by these literals. Okay, so for example, if s is 4, I will have a graph like this: y1, y2, y3, y4. Label them like y1, y2, y3, y4. Okay, so let me give you a neater picture. I will import a picture here. I will specify what L is after I explain it. Complete construction. Okay, maybe this is good enough. Okay, so there are 4 variables: x1, x2, x3 and x4. So these are the variable gadgets: x3 complement, x4 complement, and I connect them. And this clause has clause 1, x1, x2, a complete graph consists of just one edge here. There are 4 literals here. Okay, so this is a complete graph on 4 vertices, one complete graph on 1 vertex, and here 3, so complete graph on 3 vertices. So these are individually the clause gadgets and these are individually the variable gadgets. So now the question is, how do I connect them? So as the picture suggests, this x1 bar, right, this is x1 bar, so take this, connect with x1 bar, x2, connect with x2, x1, x2 bar, x3, x4, connect with x1, x2 bar, x3, x4, x3 bar, connect with x1, x3 bar, x4. Okay. That completes the construction of the graph, but I have to mention some value of L. So for that I use this. N is the number of variables. In our example, this is 4. Let us say M is the number of clauses. And T maybe the total number of literals in all the clauses. So in our example, this is 4. There are 4 variables, there are 4 clauses. And how many, what is the total number of literals? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10. As L, I will take N plus T minus M. Okay, so this is my G and this is my L. So that completes the construction. Okay. So now let me argue that this graph has a vertex cover of this size if and only if the formula is satisfiable. Okay. First of all, note that in order to cover this edge connecting x1 with x1 bar, you have to choose either this or this. Likewise, for each variable gadget, you have to choose at least one of the vertices. Otherwise, you cannot cover this or this or this or this edge. So that gives rise to these many vertices in your cover. Likewise, if I look at any clause gadget, inside any clause gadget, since this is a complete graph, if the number of edges, if the number of vertices, that is literals here, is S, I can omit at most one vertex. If I omit, for example, 2 vertices, x3 and x4, then I am no longer able to cover this edge x3, x4. But I can definitely omit just one vertex to be included in the vertex cover, and still I can cover this, all the edges inside the clause gadget. Okay. But additionally, I must be able to cover these edges which connect variable gadgets with clause gadgets. And this is where the satisfiability question comes into picture in a very subtle way. Okay. So in particular, so how many I can take from this? Total number of literals is T and there are M clauses, so T minus M. So one thing is obvious, a vertex cover of size L must consist of one vertex from each of these variable gadgets, and if a clause gadget has S vertices, S minus 1 vertices. Otherwise, I cannot reach L. Okay. Anyway, so now suppose that phi is satisfied. So take a satisfying assignment. In this case, it is, for example, x1 equal to 0, x2 equal to 1, x3 equal to 0, x4 equal to 1. So this is a satisfying assignment. Okay. Now, if x1 is 0, I will choose, since x1 is 0, I will choose x1 complement. Since x2 is 1, I will choose x2 here. x3 is 0, so I will choose x3 complement here. x4 is 1, so I will choose x4 here. Okay. So these shaded vertices, the shaded by yellow vertices, are the vertices that I choose for computing a vertex cover. Okay, so this is how I choose things like this in the variable gadgets. Now, since this assignment satisfies phi, each clause gadget has at least one true literal. Here it is x2, here it is x4. x4 is 1, x2 is 1. Here is x3 complement. x3 complement is 1. And here it is x3 complement again. x3 complement is 1. Okay. So choose any true literal. If there are multiple true literals, just choose any one arbitrarily. And do not include that node corresponding to this true literal in your vertex cover. x2, x4, x3 complement, x3 complement. Okay. And select all other nodes. Here, 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 here. There is no other node. So these are the two remaining things. So you choose them. Okay. So that is how I create the subset U. Okay. Is that fine? So take any true literal in any clause gadget and exclude that in your vertex cover. Include in your vertex cover all other vertices in the clause gadget. Okay. Except one, which is a true literal. Okay. Now, we claim that this set of vertices covers all the edges of this graph. Okay. One thing is that these edges are already covered because you have chosen one vertex from each variable gadget. Also, these edges are also covered because you have chosen just one less than the number of vertices in this complete graph. So these are covered, these are covered, these are covered, these are covered. Now question is, why are these things covered? Okay. This is fine. This is already covered. So let us look at this. You have not chosen this. So there is a possibility that this is not covered. Okay. This edge is not covered, but this is not possible because I have chosen this as a true literal. Therefore, I must have chosen this vertex in my vertex cover. So, although I did not include this, this edge is covered by this vertex. Likewise, let us look at any other thing. Maybe x3 complement. Here, I have not chosen it. But since this is a true literal, I must have chosen this. So, this edge is covered by this x3 complement here, although I do not cover it here. Okay. And of course, we may have a situation like this. Let's see. This is covered by both this and this, but that doesn't matter. Okay. Only problem could be with this, which we did not include. Okay. But since this is a true literal, I must have chosen this in the variable gadget, and therefore this edge is covered by this. So the set of vertices that I have chosen using this rule must be a vertex cover. Okay. So if phi is satisfiable, I can compute a vertex cover whose size is this by this strategy. Okay. Conversely, suppose that there is a vertex cover of size this. As I argued little earlier, we must choose one from each variable gadget. We do not have the luxury of choosing both, because then the number of vertices in the vertex cover will be bigger than L. So we have to choose one, and exactly one of this of the vertices in each variable gadget. On the other hand, it is also true that if we have the option of not choosing exactly one vertex, okay, from each clause gadget. So we can leave out one and only one. We do not have the luxury to choose all of these. Then again the number will be bigger than L, this quantity. Okay. So, therefore, I have to choose something like this. If I choose x1 complement, I will consider x1 equal to 0. If I choose x2, if I have x2 in the vertex cover, let us take x2 equal to 1. I have taken the vertex cover contains x3 complement, so I take x3 equal to 0. The vertex cover contains x4, I take x4 equal to 1. Okay. Now, suppose that I have omitted, or rather I argue it this way. So I have not chosen something like this. Okay, so this is how given a vertex cover, this is how I choose a truth assignment of the variables. Now I have to show that this truth assignment satisfies phi. Why? That's not so difficult to see, because suppose I have chosen x4 complement here and I have not chosen x4 here. Okay. Suppose this yellow is not here but here. So in that case x4 complement is 1, so that is x4 is 0. If that is the case, then you see that there is no vertex in the vertex cover that covers this edge x4, x4. Okay. So the vertex that I excluded in each clause gadget must be connected to the vertex that I have taken in my vertex cover. Therefore, it follows that each clause gadget has at least one true literal, and therefore each clause has at least one true literal. Therefore, this is 1 and 1 and 1 and 1 and so on. So this evaluates to true. Okay. If there is a problem, if we make a problem like x4 complement we have chosen, then x4 is 0, but then this edge is not covered. That is not possible, because it is given that we started with a vertex cover. So all edges are covered. Okay, so it's also complicated, but I believe it is a less complicated construction than the Hamiltonian path problem. Okay, so let us look at yet another such example. Let us look at the Clique problem. So once again you are given a graph G equal to V comma E undirected. Okay. A subset U of V is called a clique. In G, if for all U, V in U not equal to V, the edge U comma V belongs to E. So the edges of U form a complete graph inside G. Okay. Then we call this U a clique. Once again, in practice we deal with the maximum clique problem. That is, finding a vertex set as large as possible such that the complete graph induced on U resides inside G. Okay. So this is a maximization problem, but we consider this decision version. So decision version is like this. Given G and a positive integer L, determine whether G contains a clique U of size L. Okay. So once again, it is clearly in NP, because if such a clique exists, just produce that U, and then we can verify in polynomial time whether that U is a clique. On the other hand, if G does not contain any clique of size L, then you cannot have this certificate. Okay, so it's clearly in NP. Now, for proving NP hardness, I once again reduce from CNF set. Okay, so this is something like this. This time I do not have any variable gadgets. I will have only clause gadgets. So let me import the picture to establish how this construction goes. Click, yes, open. Okay, so I am converting this CNF expression, CNF formula, to a graph. Okay, so this is the clause gadget. Take two vertices x1 complement x2. Do not connect them. Okay, likewise the second one is x1 x2 complement x4. Take three vertices labeled by this x1 x2 complement x4. Do not connect them. No interconnection inside a clause gadget. And here x3, no question of connection because there is only one vertex. Now, you give connections like this. Only thing that you do not connect are the contradictory literals. Okay. So x1 complement, they are contradictory. So I do not connect them. But x1 and x2 are not contradictory, so I just connect them. x2 complement, not contradictory with x1 complement, so I give this edge, but this is contradictory to x2, so I will not connect this. x2 complement has no problem with x3 complement here. Like x4 can be connected to x1 complement, x2, x3 complement. Okay, these are non-contradictory. Okay, so this is how I prepare my graph. This construction is much simpler, and I have to also specify some value of L. L is now the number of clauses. Okay. So now I have to show that this graph has an L clique if and only if phi is satisfiable. So start with this, phi is satisfiable. Okay, so that means each clause has a true literal right? Pick any one of this arbitrarily. For example, here I have chosen, for clause 1 I have chosen x1 complement. So what is so satisfiable? So maybe this is a satisfying assignment. X1 equal to 0, x2 equal to 1. Actually I can take x2 equal to 0 also, x3 equal to 0, x4 equal to 1. So this is a satisfying assignment. And under this is not a true literal, this is not a true literal, this is the only true literal, so I have to choose this. And here x1 complement is true, x2 is also true, I just choose x1 complement arbitrarily. Here it is only true literal. Now, so you have chosen L vertices, one from each clause, okay, and you convince yourself that these vertices must form a clique. That is, if there is no edge from here to here, they are contradictory. Okay. But contradictory means this is true in this clause, this cannot be false in this clause. So, all these edges must be there. Right. If you have another clause, then take that true literal, this, they must be there. Okay, you cannot connect contradictory literals. Or if this is a true literal, this is a true literal. They cannot be contradictory. It is x4 here, it is x4 complement here, that is impossible, right? Therefore, this will be an L clique. Okay. Conversely, if this graph has an L clique, then you see that there is no connection within a clause gadget. Here. Okay. Therefore, the only way I can choose these L vertices is by picking one vertex each from the clause gadgets, like this. Okay. So, you must choose only one and exactly one vertex from each clause gadget, because inside any clause gadget we do not have any connections. So you have to choose one, and since it's an L clique, it must be that one vertex you are choosing from each clause. And then, since we have not connected vertices with contradictory labels, you convince yourself that this leads to a satisfying assignment. For example, this is my clique x1 complement, x4, x3 complement. So, I can definitely say x1 equal to 0. Okay, and we do not have any connection of x1 complement to x1. So, I will never try to set x1 to 1. Okay, because x1 complement is never connected to x1. It may be connected to x1 complement in another clause. That doesn't matter. Okay, so there is no inconsistency. Likewise, I can take x4 equal to 1, x3 equal to 0, and this assignment does not talk anything about x2, so we can take any value of x2, either 0 or 1, doesn't matter. Okay, and this choice essentially gives a true literal in each of the clauses, and therefore phi is satisfiable. Okay, so clique is once again a problem which is NP hard, and it is also in NP, so it is NP complete. Okay, so now let us do a few simpler proofs, because we have generated, now we have a bag of 5, 6 NP-complete problems. So we can use these new problems for proving the NP-completeness of other problems. So we will see a couple of examples, or maybe 3 examples. So this is the celebrated traveling salesman or salesperson problem. What does it deal with? We are given a complete graph on n vertices, something like that. That's a complete graph, undirected, on n complete graph on, let's say, n vertices. So these vertices stand for cities, and this is not only complete, this is also weighted graph. That means we will have edge here, we will have edge here, we will have edge here, edge here, then here, 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 and here. Okay. And in each edge has some positive wave, like 5, 3, 9, 18, so on. So these essentially stand for the cost of traveling from this city to this city. Okay. A traveling salesperson starts at any of the city, and his task is to visit all the cities once and only once in some order, and eventually come back to the point where he started. These are costs of traveling from city to city. Okay. So the salesperson's obvious objective is to minimize the total cost of travel. Again, you see that this is an optimization problem, a minimization problem. So this decision version is something like that. Given G and some cost C, decide whether there is a tour of cost less than equal to C. Complete tour, which visits all the cities once and only once and eventually comes back. Okay. Decide whether there is a tour of costs less than equal to C. This is definitely in NP, because if such a tour exists, give me the tour, I will verify whether the cost is less than equal to C. Okay. Or again, you can take equal to C. Okay, fine. Less than equal to C is also good. Okay. Now, this has a strong resemblance with Hamiltonian cycles in undirected graphs. So, since we know, we have proved NP-completeness of directed Hamiltonian path, and we have proved equivalence with Hamiltonian cycle problems and Hamiltonian path problems in directed and undirected graphs, it follows that a Ham cycle problem is also NP-complete. So I will make a reduction from Ham cycle to TSP. In other words, I have to take G equal to V, E, a graph. I have to convert it to another graph, G, V prime. Okay, V prime, E prime. But this E prime is now the complete set of edges along with some weight function. Okay. This does not have a weight. Okay. So we take V prime equal to V, and for an edge E in E prime, take weight of E, that is the cost of the travel, equal to 1 if E belongs to this E, n plus 1 if E does not belong to E. Then it is very easy to see that, oh, I have to also take some cost L, C. Take C equal to n. Now you see that G contains a Hamiltonian cycle if and only if there exists a Hamiltonian cycle here of cost n. So a Hamiltonian cycle of cost n uses only the edges in the original graph E. If you include any edge outside this E, the cost becomes at least as big as n plus 1, bigger than n. Okay. Therefore, it is easy to see that G contains a Hamiltonian cycle if and only if G prime contains a tour of cost n. Okay. So, I am not writing this. This is almost obvious. Okay. And there is, let's say, this problem, longest path. So once again, let's say G be a directed or undirected, doesn't matter. This time let's say this is a directed graph. ST two vertices. And edges have, let's say, for the moment assume that edges have positive weights or non-negative weights. Positive or non-negative weights. Now, you have already seen the shortest path problem, single source, all pairs. Okay, now I ask the question, find the longest path from S to T in G. In this setting, the shortest path problem has polynomial time algorithms, Dijkstra's algorithm, Bellman-Ford algorithm, then you have Floyd-Warshall algorithm, right? This longest path is a difficult problem. But we will discuss something more about longest and shortest paths in a later discussion. In any case, so now this is again a maximization problem. So I additionally give you a positive integer C. So given G and C, not only G and C, you also have S, T and C. Decide whether G contains an ST path of total cost C or greater than equal to C. Okay. Definitely, if such a path exists, I will just supply that path as a certificate. We can compute the total cost on the path and check whether it is greater than equal to C or not. On the other hand, if no such path exists, I cannot provide such a certificate. So this is clearly in NP. So in order to prove the NP hardness, I propose a reduction from D ham path to longest path. So this is G, ST. We will take G, ST. Actually, I should have a weight function and a total cost. So this should also have some weight function. Some weight function should be there and a target cost. Okay. And here I have this. Okay. So I keep G, S and T same. I am not writing G prime, S prime, T prime. This is exactly the same graph. Now you define W of E equal to 1 for all E in E and take the cost to be n minus 1. Okay, the longest path from S to T is of cost n minus 1 or more, actually equal to n minus 1, if and only if it is an Hamiltonian path from S to T. Okay, that is clear. So proving NP completeness after we have many problems in our bag is not now becoming so difficult. So I will just end with another example. This is independent set. This is just the opposite of Clique. So G equal to VE undirected. And U, subset U of V is called independent. If UV in U not equal to V, let's say, implies UV in Clique we had belongs to E, now I have not belongs to E. Okay. Independent set. Okay. Clearly this is an NP because if really there is an, okay. So again, actually you want to find a maximum independent set or something like that. In any case, so the decision version is given G and some L, decide whether G contains an independent set U of size U equal to L or greater than equal to L, doesn't matter. Okay. So if an independent set of this size exists, then just provide this set and in polynomial time I can verify whether that's really an independent set. On the other hand, if G does not contain an independent set of size L or more, then I cannot have this certificate. And for proving NP hardness, I will simply make this obvious reduction from Clique to independent set. Okay, Clique has G, whether G has a clique of size L. Okay, from this I will make a graph G prime. Keep the same value of L, and this reduction is if G is VE, G prime will be, I will keep the same vertex set and basically the complement of E. Okay, so an edge exists in G if and only if it does not exist in G prime. Okay. Then G contains a clique of size L if and only if G prime contains an independent set of size L. Okay, that is fairly trivial and obvious. Okay, so this edge set is the complement of E in the set of all possible edges over V. Okay, so this way, okay, so we therefore have seen quite a few, I would say, examples of NP-complete problems. In particular, we now have the following tree. Initially, we started with SAT and CNF SAT, but proving their NP completeness or NP hardness is so difficult, we didn't cover. Okay. From this, we have seen Hampath, and equivalently our Hem cycle, D-Hem cycle, these problems. Today we have seen Vertex Power. Then we have Clique. Okay. From this or one of its equivalent versions, we have proved longest path, TSP as NP complete. From this, we have done this independent set problem. And this thing goes on. Okay, we may reduce this further, this further, this further, and then new problems again from the reduction. So this way, the tree of NP-complete problems grows. Okay, and now literally thousands or maybe tens of thousands of problems do reside in this tree. We have made NP-completeness proofs. Okay. Some are very difficult, like this to start with, and these were also quite difficult, whereas these last three proofs were fairly intuitive and straightforward. Again, when you come up with a new problem which you prove to be NP-complete, it is possible that you make a simple reduction, but it is also possible that no such simple reduction immediately is possible. You may have to make much more complicated reductions like this, and so on. Okay. Even if you start at a larger level, maybe from longest path you are converting to your new problem, but that proof itself need not be very easy. Okay. Anyway, this is how life goes, and there is a necessity to identify the most difficult problems in the complexity class NP, and you see that many of these problems are very useful problems. Traveling cis-person problems, longest path problems, independent set problem, vertex, these are all very useful problems, but we already know that these are NP complete. So unless P is equal to NP, we do not know how to solve these problems easily. But since these are important problems, we have to solve some of this. Okay. So, big question is, knowing that something is NP complete, knowing that some problem pi is NP complete, how can we solve pi? Of course, this is a big question. In general, we cannot solve, but if it is an important problem like the traveling salesperson problem, we should do something. Okay. So after this chapter, we will study what we can do to so-called solve within quotes NP-complete problems. Okay, for the moment, let me stop here today. Bye.